Okay, on page 432 you have 4 problems. For number 1, tell whether each equation is the inverse of f of x equals x cubed minus 16. So let's find the inverse of this one. We would say y equals x cubed minus 16. I'm going to add 16 because I'm solving for x. So y plus 16 is x cubed. Find the cube root of each side. So now cube root of y plus 16 equals x. Switch the x and the y. And so now you write f inverse of x equals cube root of x plus 16. So that one is letter B. Okay, for number 2 we have to say whether each statement is true or false. So for part A, this is a square root function. It has that same shape as a square root function. H is 1 right here, and K is negative 2. So that means that the starting point should be at 1, negative 2. And if you see right here, this is 1, negative 2. And it is opening up towards the right, so this one would be true. For part B, it's asking whether the function has exactly one y-intercept. Well, actually this one is false because it has no y-intercept. It's never, ever, ever gonna cross over here on this side because the arrow is going to the right. This is a dot where it starts, so it's never gonna come over here on this side. So B is false. Okay, for C, it says the range is y is less than or equal to negative 2. Well, that would mean that the graph is opening down like this, but it's actually going up like this. So if I go from bottom to top on the y-axis, my first y on my graph is actually at negative 2, right here, it's right here, and then it goes up from there. So this one is also false, because it should be y is greater than or equal to negative 2. So for number 3, they tell you that the average rate, or the average speed of a plane going from one city to another is 550 miles per hour. So that would be like this one, going from point A over here to this side. And then on its return trip, it travels at 430 miles per hour. They want you to find out what is the average speed of the plane over the entire trip. So the plane went and then it came back. So it traveled this distance plus this distance, right? So in this whole distance, it went 550 miles per hour. Over here they went 430 miles per hour. So because the distances are the same, because it started in the same city and ended in the same city, then we could take the average of the two speeds. So 550 plus 430. And take, average, you add the 2 and divide by 2. And so that's going to give you 980. Divide by 2. So that's going to give you 490. So that's the average speed of the entire trip. Of going to the city and coming back. For number 4, they want you to find the inverse model for this equation. E is the kinetic energy and S is the speed of the car. So when you're dealing with real life equations or real life situations, you don't follow the 4 steps when you're looking for the inverse. Basically what we're doing here is we're going to solve for S, and we're not going to be switching the E and the S, only we're going to be solving for S, and that will represent the inverse model for this situation. So the first thing we're going to do is divide by 625. Okay, and so now we have E over 625 equals S squared. Well, we want S by itself, so we're going to take the square root of both sides. So now we have S equals square root of E over 625 is a perfect square. Its square root is 25. Okay, so this is the inverse of this. Okay, so these two are inverses of each other. Now the second part of the equation is if the kinetic energy doubles, will the speed double? Okay, well, let's say that we put in 25 for the kinetic energy. So let's say that E is 25. Okay? So if I put in 25 versus putting in 50, right? It says if we double the energy, will the speed double? Well, if I put in E equals 25, square root of 25, so S is going to be square root of 25 over 25. So that's 5 over 25, which is 1/5. Okay. Over here, if we put in 50, and I just picked those two random numbers, okay? I just picked 25 because it's a perfect square, but then I have to double it, so that gives me 50. So square root of 50 over 25. Okay, so 50 is 25 times 2. So the 5 comes out, the 25 comes out as a 5. So this is going to give me 5 square root of 2 over 25, which is square root of 2 over 5. Sorry, I have to reduce 5 right here and here. So compare this number to this number, it's not double. It's actually square root of 2 times. It's not 2 times. So the answer would be no. If you double the kinetic energy, the speed does not double. It's a little bit less because it's radical 2 times bigger, not 2 times bigger. Okay, for number 5, they're asking you to graph the function. This is based on the fetch versus the fetch is the length of water over which the wind is blowing in a certain direction, and S is the speed. So S is the speed of the wind in kilometers per hour, and the fetch F is the length of water over which the wind is blowing. So when you graph that, because they're asking you to graph it, so I would use Desmos.com to graph this just because it's kind of a messy function because you have 7.1 and they want you to extend it all the way to 140 and 200. So graphing it by hand would be very tedious. So I just put it into a graphing calculator, and this is what the whole function looks like. Let me just kind of do a rough sketch. It's something like this, right, because it's a cubic function, but because it's dealing with a real life situation, you know, the speed and all that, we don't include, because there's no negative length of water, right? Because this right here, the x-axis, I keep calling it x-axis, but in this problem it's not really x-axis, it's f, and right there this is the s, the speed. So the horizontal axis, this one right here, is the length of water over which the wind is blowing, and the vertical axis, which is usually our y-axis, is the speed of the wind. Well, length of water is not negative, right? So we're gonna just ignore all of this and just focus on this right here. Okay, focus on that piece. Okay, so the easiest thing to do for this problem, if you have a graphing calculator that has the table feature, then that's cool. That would be as easy as what I'm going to show you right now. But they want you to calculate the average rate of change from F20 to 80, then from 80 to 140, and then from 140 to 200. So the easiest thing to do for this is just make a table, F and S, and use your calculator. So I'm going to put 20, 80, 140, and 200. And why am I choosing these? Because this tells me right here the range that they want me to go from 20 to 80, 80 to 140, 40 to 200. These all represent F values. These are intervals. So I'm going to put in a 20 for F and then just take a calculator and plug it in. The cube root, all scientific calculators have a cube root button that you can use to figure it out, and then whatever you get times 7.1. Alright, so I went ahead and I took a calculator and figured out the value of S for those 4 values of F. Like I said, using the cube root button or the nth root key on the calculator. We'll go over it in class tomorrow if you can't find it on your calculator. But anyway, this is the formula for the average rate of change. This represents like the y value when x equals, for the second point. And this is the y value for the first point, and then this is your x. So it's a formula for slope, just in a different notation, but it's basically difference in the y's over the difference in the x's. So I'm going to go, they want you to go from 20 to 80. So the 20 to 81, we'll do that one first. So at 80 I got 3059 minus at 20 we got 1927. I'm writing the S values over 80 minus 20. So this is going to give you 60 down here. And then in the numerator we just subtract 3059 minus 1927. So that's 1132 divided by 60, so it's 0.1887. Okay, then we'll do the one that goes from 80 to 140. So I'm just writing it down right here so we have keep the information organized. So from 80 to 140, so it's going to be 140 is the second point because that's your last point. So I'm going to put 36.87 minus 3059, which that's a 1 for 80, over 140 minus 80. So that gives us 60 in the denominator. And then 3687 minus 3059, that's 628. So that's approximately equal to 60, so that's 0.1047. Okay, and then move it a little bit. From, because I ran out of room, from 140 to 200, from 140 to 200, we take the number for 200, which is 4152, and then the number for 140, which is 3687, and then subtract 200 minus 140. So that gives us 60 in the denominator, and 4152 minus 3687, so that's 465. It's a 65, right? So then we divide that by 60, and we get approximately 0.0775. Okay, so these right here are the average rate of change for each interval. Notice how the number is getting smaller and smaller. Okay, so it says what's happening to the average rate of change as the f values of the intervals increase. The average rate of change is getting smaller. Why? Because notice initially over here the graph grows faster, and then as you go out it grows a little bit slower. It doesn't increase as fast. So here it increases really fast, but then it slows down. Still increasing, but slower. And then use the function to find the speed of the wind when f is 64. So they want you to do it's S of 64, so that means 7.1 times the cube root of 64. So the cube root of 64, you know, is 4, right? Because the cube root 4 to the third power is 64. So this is 7.1 times 4